So in today's class, we're really going to be focused on what happens when we don't have alkanes reacting with radicals anymore, but what if we have alkenes? And two different things can happen. One is that you can get an addition reaction. So that happens if we have HBr with light, heat, or peroxides. Remember, ROOR means it's some sort of peroxide compound. We can have a pretty standard addition. We'll see in a later video how this differs from the acid addition of HBr that you probably saw in 331. But what we end up having is just we lose their alkene, we add hydrogen to one carbon, bromine to the other. But if we use this special reagent NBS, which we'll see in multiple chapters this semester, we'll talk about what that is soon. What we get is instead of an addition to the alkene, we get a substitution, and we get that substitution specifically at the carbon next to the alkene. We call this an allylic carbon, the allylic position, and we'll talk about that again much more coming up. And so what we get is that the hydrogen at that specific position is replaced with a bromine, just like we saw with our halogenation of alkanes last class. And so what you would expect to see here is this. And so notice that the reagent that we choose is different. HBr signals addition, NBS signals an allylic substitution. So now we're going to think about the allylic halogenation in a little bit more detail. So to do that, first we have to sort of reconsider our radical stability. So last class we talked about how the increasing alkyl substitution increases radical stability. So a primary radical is more stable than a methyl radical, secondary is even better, and tertiary is even better. And now we can say that an allylic radical, one where the radical is on a carbon next to a double bond, is even more stable. And the reason for this is because that radical doesn't exist on one carbon, but it's shared due to resonance. So let's look at this structure in a little bit more detail. So here we have a radical and we have a double bond. And we can imagine drawing a second resonance structure for this. Remember, because we're only moving one electron at a time, we have to use these special half arrows. And what you can see is that that radical can combine with one of the two electrons in the double bond to make a double bond here and put a radical on this carbon instead. And so what happens is that that radical character is shared between those two carbons. Remember, when we're dealing with resonance structures, neither one of these resonance structures is the true structure. What's true is that overall we have a hybrid structure where these three electrons are shared among these three atoms. And this has a partial radical character. This also has a partial radical character. The carbon in the center doesn't have any radical character at all. So this hybrid structure is the true structure, but it doesn't give us as much information in terms of arrow pushing or other things, so we don't often see it. But just because we don't see it doesn't mean it's not important. We'll see much more of these delocalized structures in chapter 14. So as practice, I want you to be able to draw the other resonance structure here. So pause the video, draw that. The other resonance structure here is going to be one where we, again, do the same sort of arrow pushing. This electron combines with this one. Another electron goes towards the end. So here you're going to notice that if we look at these resonance structures separately, this one looks like a secondary radical, this one looks like a primary, but remember, the true structure is the hybrid, but what this means is that these two different carbons both have radical character. The secondary carbon and the primary carbon both have radical character in the true hybrid structure. So now we're going to look at the mechanism of this allylic halogenation. And to do that, I first want to talk about what this reagent is. You do want to memorize that NBS is what does allylic halogenation. Here's the structure of NBS, which I don't necessarily want you to memorize. So NBS is N-bromosuccinimide. And the two things that are very important about this reagent is one, that this NBr bond is very weak. That is going to form the first radical in our initiation step. But the other thing is that NBS is going to react with HBr, which we'll see produced in the reaction to produce small amounts of bromine. That bromine is going to play a role in our reaction also. And the reason why it's important that we use NBS and not bromine directly is that bromine can react with alkenes in the reaction you learned in 331. So we know that bromine can form a bromonium ion, which is then attacked by bromide anion to form something like this, where the bromines are on opposite sides of the ring. And this happens with high concentrations of bromine because you need 2 molecules of bromine, second order bromine, to make this reaction happen. So the fact that we have small amounts of bromine produced by NBS means that we can suppress this unwanted side reaction. So our first step of our radical reaction here is the initiation, and this comes from the homolysis, the splitting of our NBS. And this can happen just in light. So we don't need to add peroxides to make this happen. It's a weak enough bond that this will just happen on its own to produce 2 radicals. One is this nitrogen-centered radical that we have here. The other is a bromine radical. And remember, bromine has 6 other electrons that aren't that radical. And then this is what's going to go on to our propagation step. So this propagation step is where our alkene actually comes in for the first time. I'm going to use a very simple alkene for reasons that will become very clear on the next slide. And I'm just going to choose one of the 2 identical allylic hydrogens. So this is going to react with our bromine radical, and it's going to undergo a hydrogen abstraction. Remember, the weakest CH bond is the one that makes the most stable radical. And so this CH bond, the allylic one, is the weakest bond around. So that's going to react with our bromine, and then it's going to create a carbon-centered allylic radical in the next step. So here we have our allylic radical, and the reason why I chose this very simple alkene is because both resonance structures are identical. Our side product here is HBr, which we said before will react with NBS to give us small amounts of bromine. So we can just say that we have bromine coming in. We don't have to actually show in our mechanism that bromine being produced. So this radical is going to break up our bromine to form a new carbon-bromine bond and create another bromine radical, just like we have in this first step. And that's how propagation tends to work, is you create a new radical that can keep going. And so this propagation step will happen basically until our alkene runs out. So we have this bromine radical. This bromine radical is going to go on to react with more allylic hydrogens, and we have our final product. There will be some sort of termination step. We don't necessarily need to show it here because our reaction is already finished. We've already brominated our allylic position. We're not going to see this with any other halogens. No fluorine, chlorine, or iodine here, only bromine. So at this point, I'm hoping that you can successfully predict the product for this first reaction. So if I give you NBS and light, you know to find the allylic position, and that's where the bromine is going to end up. So you're going to end up with the same cyclohexene, but now with a bromine, 1 carbon over from the alkene. But if we do the same products for this molecule down here, we're going to get some surprising results. So we'll get one product that we probably would expect, which would look like this, where we have the bromine 1 over from our double bond. But we'll also see a second product, and that product is going to look like this, where the bromine is on the end of the carbon chain, and we have a double bond here instead. And so where is this coming from? To see this, we have to think about the radical formed. So the intermediate in this mechanism is going to be our allylic radical, which looks like this. That allylic radical, remember, is truly a hybrid. There are 2 forms. So this is one form. The other form has the double bond here and the radical on the end. So this allylic radical, really both of these structures truly represent the allylic radical. And so we should get products from both carbons with allylic character, with radical character, which are this one and this one. So we see that we form products here and here, where that's where we get our bromine. I really want to caution you against treating these 2 resonance structures as different molecules. It's so easy because they look different, but they really are representations of the same hybrid molecule, which would look something like this, where we have the 3 electrons distributed here, with a partial radical character there and there. So I want you to practice this on your own. There are 2 products here. Pause the video, write them. We'll come back and talk about this. So again, our allylic system, we have an allylic hydrogen here that can be removed. This carbon over here has no hydrogens. It's a quaternary carbon, so there's no hydrogen to be removed. We don't have to worry about it, which is good because that might make the problem even more complicated. So our 2 places with radical character are going to be here and here, which we can see if we draw our intermediate. That intermediate is our allylic radical. So I'm going to draw that here with a second resonance structure that looks like this. So both of these places where there's radical character are going to get a bromine. So I'm actually just going to erase the intermediate and just put bromines wherever I have radicals. So I'm going to put a bromine here, try to overwrite that radical, and one here. And I'm going to have to erase, I'm just going to make this thicker. So those are our 2 products.